Okay, everybody, before I finish chapter 7, since it's been quite a while, I'm gonna just do a little quick review on the stuff that I've already gone over in class. And let's quickly go over some of the material. Then, how do you know if there has been a chemical reaction or not? Sometimes you will see it by naked eye, sometimes you cannot see it. Then if you cannot see a chemical reaction, you cannot immediately assume there has not been any. There are ways for you to be able to prove it to yourself that whether there has been a chemical reaction or not. These are some of the examples of chemical reactions. The first one, this one, okay, as you could see, it's a precipitation reaction, and as you could see, two solutions in the aqueous state being added to each other, and you will have precipitant as a final product. Then this yellow precipitant that you see at the bottom of the beaker, it's a formation of a precipitant, which is an indication of a chemical reaction. And the second picture is the formation of fire. Like if you drop a piece of sodium or potassium in water, the metal immediately reacts with water and it produces fire because it produces a lot of heat, and that's formation of fire is one of the indication of chemical reaction. Acid-base titration is also another indication of chemical reaction. Like in some of these examples, sodium hydroxide, which is an acid, which is a base, react with hydrochloric acid, which is a strong acid, and there is a change in color. One other one is gas formation. For example, if you put calcium in water, you will see all this bubbling forming, and that's an indication of formation of hydrogen gas. Okay, that's also indication of a chemical reaction. Now, whenever we have a chemical reaction, we have a chemical change. If you recall chapter 3, when we have a chemical change, that means one reactant convert to another reactant, okay? Or one substance convert to another substance. Then if you look at this particular example, calcium reacts with liquid water and it produces calcium hydroxide and hydrogen gas. Then as you could see, these reactant reacted together and they produce product. We also have rearrangements of the atom. Then as you could see here, calcium is on its own, hydrogen is bonded to two hydrogen to one oxygen, and we will have calcium hydroxide and hydrogen gas. Then these are all indication of chemical reaction which leads to chemical change. However, when we have only a change in the state, like this particular example right here, you see we're going from solid water to liquid water and then to gaseous water. Okay, this is not a chemical change, it's a physical change. Let me write it down and get, okay, that's a physical change. Physical change. Okay. All right. Then when we have a chemical reaction, there is breaking in bond. That refers to the reactant, and we have a formation of new bond in the product side. Okay. Then this is the example that I went over in class. Methane gas reacts with oxygen gas. It produces carbon dioxide and liquid water. Okay. Then as you could see, there is the bond between carbon and hydrogen all broken down. The bond between the two oxygen is broken down, and then we will produce new bonds between carbon and oxygen and hydrogen. Okay. Then that's what it means by breaking old bonds, which is the reactant, and forming new bonds, which forms product. And all these numbers, these are coefficient that we use to balance chemical reactions. This is the example that I just went over in the previous slide, which shows if the old bonds are broken, new bonds are formed. Then to show a chemical reaction, we use chemical equations. Okay, whenever we are writing chemical equations, we have to use a series of symbols. Then as you could see in this particular example, reactants are always on the left hand side of the arrow, products are always on the right hand side of the arrow. Also, we use coefficient to balance our chemical equation because we have to follow the law of conservation of mass, and based on the law of conservation of mass, we cannot have any missing atoms or creating any atoms. That's why we use coefficient to make sure we have the exact same number of each species, whether it's a reactant or product, on each side of the equation. These are some of the symbols that's being used when we are writing chemical equations. Arrow, which always goes from the reactant side to the product side. If you have formation of heat, use delta. Whenever we writing chemical equation, we have to always show the state of all your reactants and products. And if it's a solid, if we use lowercase s, liquid lowercase l, gas lowercase g, and aqueous solutions, it's AQ. Then we've already talked about aqueous solution, which means your solvent is water. Like this example, if you dissolve solid sugar in liquid water, the states become aqueous. That means the solvent has been water. Then just go over law of conservation of mass one more time. Is no atoms are created nor destroyed. Then we use those coefficients in front of each of the reactants and products to balance our chemical equation. Okay, we call it coefficients. Then the first thing that we want to do when we are balancing chemical equation is to write the equation with the correct formula. Then if for this particular example, there is a reaction between methane with oxygen gas, which produces carbon dioxide and liquid water. Okay, and as you could see, I put the state of each of these reactants and product. Okay, now the next thing that we're gonna do is to balance it, which we did. Then if I go back here to the previous slide, I had one carbon on the reactant side, one carbon on the product side. I have 4 hydrogen on the reactant side. I had 2 hydrogen on the product side. We had 2 oxygen on the reactant side, whereas I have 2 and 1, 3 oxygen on the product side. Then as you could see, this equation is not balanced because we do not have this exact same number of each species on each side of the equation. That's why we ended up balancing the chemical equation. Then if you add a coefficient 2 in front of water, I told you guys, whenever you are balancing chemical equation, okay, do solids on its own, like elements on its own, that's what I mean. Elements, diatomic compound, balance it last, because whatever you do, it's not going to mess up the other elements. But here, carbon is balanced, you don't have to do it. Then between hydrogen and oxygen, since oxygen is diatomic, we're going to do it last. That's why we do hydrogen first. Then since we have hydrogen and 4 hydrogen on the reactant side, if you add a coefficient 2, you will have 4 hydrogen on the product side. And then that makes that 2 and 2, which is 4 oxygen. And if you add a coefficient 2, you will also have 4 oxygen. And as we did before, this equation is now completely balanced because we have 1 carbon on each side, 4 hydrogen on each side, and 4 oxygen on each side. And that's what we have to do. We have to check to make sure that we have the same number of each reactants or each element on each side, which we did. We did a series of problems in class. I'm not going to go over them, but if you have any question, please let me know and I will go over it with you. And I did 1, 2, 3. These are the examples I did. The next thing is about indication of chemical reaction. Just going back, and we're going to talk about every single reaction. Then the first one that I'm going to talk about is the formation of solid, then which we call it precipitation. That's the formation of solid. All right. Then whenever we have a precipitation form, that means one of your product is a solid. And I gave you that pink handout in class, which shows you it's a solubility rule. It says which of the products will be soluble, which one will be insoluble. Then if it's soluble, the state of it is in aqueous. If it's insoluble, the state of it will be solid. Okay. One thing that it's a good idea to pay attention is that you do not always get precipitation when you mix solutions. Sometimes you have precipitant as a product, sometimes you don't have. Sometimes all your reactants and products will be in aqueous state, which is also fine. Okay, now how do we write a product using two reactants? Okay, then here there's a reaction between potassium iodide and lead 2 nitrate. Then what happens is that potassium iodide is made of potassium ion and iodide ion, and lead 2 nitrate is made of lead 2 ion and nitrate ion. Then what happens is that, as you could see in this example that I went in class, the cation from one of the reactants react with the anion of the second reactant, and the anion of the first reactant reacts with the cation of the second reactant. Okay, that's why the products for the reaction between aqueous solution of potassium iodide and lead 2 nitrate will be potassium nitrate and lead 2 iodide. Now, once you have that figured out, the next thing that you want to do is to state of it. You need to know whether the state is in aqueous or is in solid. Okay, then look at the solubility handout. If you look at the solubility handout, you will see, let me get my solubility handout out, give me a second. Then based on the solubility handout that I gave you in class, then look at where it says, like the second paragraph says mostly soluble compound. It says any cation with either chloride, bromide, iodide is soluble, that's soluble, with the exception, and lead is part of the exception. Okay, that's why lead 2 iodide, it will be in solid state. Okay, now let's look at potassium nitrate. Potassium is group 1. Then if you look at the top of the solubility rule handout, which says soluble compounds, it says group 1 cation with any anion forms a soluble product. That's why the state it's soluble means is in aqueous state. Okay. And then once you know the state of each of your product, the next thing that you have to do is to balance it. Okay, to make sure that you have the same number of each element on each side of the equation. And I did a series of examples. Again, if you're not sure, please contact me so that I could go over it with you one more time. And then I talked about the 3 type of equations: molecular, ionic, net ionic equation. Then what we're gonna do, we're gonna write the complete ionic, net ionic, and total ionic. As you can see here, complete equation is sometimes referred to balanced molecular equation. You will see it. It's just the same thing. Then we're going to write a complete ionic, net ionic for the reaction between silver nitrate and sodium chloride. Okay. Now let's write a complete or balanced molecular equation for this reaction. Okay. Then the first thing is just basically writing your chemical equation and writing the state of each of your products. Okay. Then this will be your balanced molecular equation, and you have to make sure that's balanced. The next one is to write ionic equations from balanced molecular equation. Then when you are writing ionic equations, for you to know which species they're going to form ions, which species will not form ions, is if you have aqueous ionic compounds, then if your compound is ionic and it's in aqueous state, it will separate. If not, it will not. Or basically, all solid liquid gases, weak acid, weak bases do not separate. Molecular compounds in any state will not separate. Okay, then the only ones that they will separate, should write it here, separate, are ionic compounds in aqueous state. And I don't know why my pen skips, but I apologize for that. Strong acids and strong bases. Okay. Then they will separate. Then if I go back to my previous example, when we are writing ionic equation from a balanced molecular equation, you're going to treat each species as if nothing else exists. Then look at silver nitrate. Ask yourself what kind of a compound it is. Then you know it's ionic because it's made of cation and polyatomic anions. Okay. Then once you know it's an ionic compound, look at the state of it. It's an aqueous. Then it will separate. Then you will produce silver ion and nitrate ion. Then go to the next one, sodium chloride. Sodium chloride is also ionic compound and the state is in aqueous. That's why it will undergo separation, which will produce sodium ion and chloride ion. Now let's do the product side. The first product is silver chloride. Silver chloride is an ionic compound, but look here, the state is in solid. That means it will not separate. We leave it as is. Sodium nitrate. It's an ionic compound. It's in aqueous state. That means it will undergo separation, which produces sodium ion and nitrate ion. Once you have your ionic equation written, the next thing that we want to do is net ionic equation, which means we're going to get rid of the spectator ions, which means those ions that repeat themselves on each side of the equation is your spectator ion. And spectator ions do not participate in the reactions. Then if I go back to my equation, the nitrate ions, they are repeating themselves on each side. Okay, let me change the color of my pen. Let's go red. The nitrate ions are repeating themselves. Also, let's change it to this color. Sodium ions are also repeating themselves. And these are your spectator ions, nitrate ion and sodium ion. Then whatever is left over will be your net ionic equation. Okay, this is the net ionic equation for the following, for above reaction. Also, one thing that you have to pay attention, that you don't need to touch your net ionic equation. If, for example, you had to balance your net ionic equation, that means you made some mistakes in the previous equations, which you need to go back and make sure to fix it. If you've done everything correctly, your net ionic equation should not need any balancing. Okay, and I did some examples. Right, that's where I stopped. Okay, you're gonna write a complete total ionic and net ionic for the reaction between potassium phosphate and sodium carbonate. Let's do that one. Let me get my notes out. All right. then the first thing that we want to do, we're gonna write a balanced chemical equation between these two reactions. Potassium phosphate, it's K. Let me change my pen. Okay. I'm sorry. This is potassium sulfate and sodium carbonate. Okay. Then potassium sulfate. Okay. And sodium carbonate. These two are in aqueous state. Okay. Now let's write down the products. Remember, the cation from one of the reactants react with the anion of the second reactant and vice versa. Then we will produce potassium carbonate, Then if you look at the solubility handout, you will know the state of potassium carbonate is in aqueous state, because all group 1 cations, they produce soluble compounds. Okay, and the same thing with sodium sulfate. Okay, it's in aqueous state. Then this is your this is your balanced molecular equation. Okay, one thing that you want to know, this is already balanced, but just to double check it, we have two potassium on each side, we have one carbonate ion on each side, two sodium on each side, and one sulfate ions on each side. Remember, when we are doing atomic ions or oxyacid ions, just balance it as whole. You will say I have one sulfate ion on the reactant side, one sulfate ion on the product side. That's how we do it. Okay, then this is already balanced. I don't need to balance it at all. Then the next thing that we want to do is to write ionic equation. Okay, let me change my pen. All right, now let's look at potassium sulfate. Potassium sulfate is an ionic compound. It's in aqueous state, then it will separate, and it produces plus SO4 2 minus. Okay, then you have to indicate, since we have two potassium ions, that's why I put the coefficient 2. You also have to indicate the charges. Okay, you also have to write down the state of each reactant. Then let's talk about sodium carbonate, which again, it's an ionic compound. It's in aqueous state. That means it will separate, which produce 2 sodium ion plus carbonate ion. Okay. Now let's look at the product side. For the product side, let's talk about potassium carbonate. It's an ionic compound. It's in aqueous state. The ionic compounds in aqueous state, they will undergo separation, which produces 2 potassium ion plus carbonate ion. Okay. Now let's do sodium sulfate. Again, it's an ionic compound in aqueous states. That means it will undergo separation, which produces 2 sodium ion. Let me fix this one. SO4 aqueous, and I go here. Okay, 2 sodium ion plus right. Then this is your ionic equation for the above molecular equation. Now let's look at the spectator ions, because we need to write down the net ionic equation. Then as you could see here, everything cancels out. The 2 potassium ions cancel out. The sulfur ions cancel out. Let me choose one other color. The sodium ions will cancel out, and the carbonate ion is also canceling out. Therefore, we have no net ionic equation, which is totally fine. Okay, then whenever all your reactants and all your products are in aqueous state, ionic compounds in aqueous state, you will not have any net ionic equation. Okay, just to take a note of that. Okay, sorry, I think I jumped. Let me write it down here. Okay, when sorry, I think I messed it up. Let me go back. Okay. When all reactants and all products are ionic compound, compounds in aqueous state, therefore no net ionic equation. Okay. So when all reactants and all products are ionic compound in aqueous state, we have no net ionic equation. Right. This is exactly the same thing. Okay. Here we have sodium chloride. Okay. Reacts with potassium nitrate. Okay. Which produces potassium chloride and sodium nitrate. And if you look at your solubility handout, these two products are both in aqueous state because they are these are group 1 cations. Then group 1 cation with any anion produces soluble compound. Okay. Then this is and then you have to balance it. This already is balanced because as you can see here, we have 1 sodium on each side of the equation. We have 1 potassium on each side, 1 chlorine, and 1 nitrate ion. Okay, it's already balanced. I don't need to balance it. The next thing that I'm going to do, this is our balanced molecular equation, is to write the ionic equation. Okay, now let's do the ionic equation. Right? Then sodium chloride is an ionic compound. It's in aqueous state. Then it undergoes separation, which produces sodium ion plus chloride ion. Potassium nitrate is the same thing. It's an ionic compound. It's in aqueous state. It produces potassium ion and nitrate ion. Now for the product side, potassium chloride is an ionic compound. It's in aqueous state. Then again, it will undergo separation, which produces potassium ion plus chloride ion, and then sodium nitrate, which is also again an ionic compound, and it's in aqueous state. Then produces sodium ion plus nitrate ion. Okay, then this is your ionic equation for the above balanced molecular equation. Then as you can see here, next we're going to write your net ionic equation. As you can see here, then sodium ion, we have it on each side. We have chloride ion on each side. We have potassium ion on each side, and we have nitrate ion on each side. Then as you could see, all the ions are spectators ion, and therefore we have no net ionic equation. Remember the previous note that I wrote? When all your reactants and products are ionic compound in aqueous state, we have no net ionic equation. Okay, that's the second example that proved that. All right. Now, let's talk about acid-base reaction, which was the second reaction on that list. Then when we have an acid, hydrochloric acid is an acid, reacts with the base, okay? Then when you have OH at the end of a chemical formula, that's a base. It produces liquid water and sodium chloride. Just know that. Then regardless of the strength of your acid or base, whenever you have an acid reacts with the base, your product is always liquid water and aqueous salt or aqueous ionic compound. Salt or ionic compound. Okay. Okay. Now, acids, they carry hydronium ion or hydrogen ion. Okay. You see that? That's an acid. We refer to hydrogen ion as in hydronium ion. This one, okay, then what happens is that hydrogen ion is very unstable. Then it reacts with liquid water and it produces hydronium ion. Then if you plan on taking 180 and 185, the department requires you guys to refer to hydrogen ion as in hydronium ion. It's not wrong. A lot of other places they refer to it as hydrogen ion, but for our department you have to refer to it as hydronium ion, which is H3O+. Then acids, they carry hydronium ion. Okay, this is the list of your strong acids, which you need to know. Okay, these are all the strong acids which you need to know and memorize. Then everything else will be weak. Okay, then remember the list of your strong acids. Then all these 3, 4, 5, 6 are strong acids, and also it means they undergo complete ionization. Okay, then the weak acids, they do not. You could say they do not separate. Okay. What I mean is that when you are writing an ionic equation, then if your acid was a weak acid, it does not separate. If it was a strong acid, it will separate. or will separate. Okay. Now bases. Bases, they carry hydroxide ions, OH minus. Again, this is the list of all our strong bases, which you need to know, and the rest will be weak base. Then strong bases, they do separate, and weak bases do not separate. Okay? All right. Then again, whenever we have an acid, regardless of the strength of your acid, reacts with the base, regardless of the strength of your base, your product is always liquid water and aqueous salt, or ionic compound in aqueous state. Oops. In aqueous state. Okay, just know that. All right. Then whenever we have strong acids react with the strong base, for example, we have hydrochloric acid, which is a strong acid, reacts with, sodium hydroxide, which is a strong base. Okay, it produces sodium chloride. Then what happens is that this chlorine reacts with the sodium, which produces sodium chloride plus, and the hydrogen from the acid reacts with hydroxide ion of the base, which produces water. Okay, that's typical neutralization reaction, because the pH of your solution will be 7. Then if this is a pH scale, it goes from 0, let me make it bigger. It goes from 0 to 14, the midpoint is 7. Then if your pH is less than 7, the environment is acidic. Okay, and if the pH is greater than 7, or it's between 0 to 14, it's basic. Okay, and if it's exactly at 7 at this point, exactly, it's neutral. Oops. That's why when we have a strong acid reacts with a strong base, the pH or the environment, the pH of your environment is at 7. Okay, 7 is a neutral pH. Also, whenever you have strong acids react with a strong base, this is always your net ionic equation. Okay, this will always be the net ionic equation. Why would it be? Because this is your balanced molecular equation, right? And it's already balanced. I don't need to balance it. Now let's write the ionic equation. Okay, ionic equation. Now let's write it for hydrochloric acid. Hydrochloric acid, it's a strong acid. It will undergo ionization. Okay. Then remember, I told you guys write hydronium ion instead of hydrogen ion. Then that's what we're gonna write. H3O plus chloride ion. Okay. Then whenever we write hydronium ion, to balance the hydrogen and oxygen, we have to add 1 molecule of water on the opposite side. Then if you add 1 hydronium ion on the reactant side, you have to add a molecule of water on the product side. Okay, don't forget that. Then I added 1 hydronium ion, which is produced from hydrogen ion up here. Okay, that's a strong acid. It will undergo separation or complete ionization. Then it produces hydronium ion and chloride ion. Rule number 2, for every hydronium ion that's produced, we add a molecule of water on the opposite side. Okay, keep that in mind. Now, sodium hydroxide, it's a strong base. It will undergo separation, which means it produces sodium ion and hydroxide ion. Okay, now look at the product side. Sodium chloride. What is it? Ionic compound. What's the state of it? Aqueous. Remember, ionic compounds in aqueous state, they will undergo separation, which produces sodium ion plus chloride ion. Okay. Last one, water. Remember, solid, liquid, gases, they do not undergo separation. This is also a molecular compound. Okay, then write it as is, then it will not separate. But remember, I said for every hydronium ion that we produce, you have to add a molecule of water. Then 1 is coming from here and 1 is coming from the production of hydronium ion. That's why instead of 1 water molecule, we have to have 2. Okay, that's why I have 2 water molecules. Okay, then 1 is coming from the reaction of our acid and base, and the second one is coming due to the fact that we produce hydronium ion. That's why we have 2. One thing that you should not do is you should not go back and make that 2, because if you go back to your balanced molecular equation and make it 2, then you will mess up your hydrogen and oxygen. Leave that untouched. That's only for your ionic equation. Okay, and then for the spectator ions, then chloride ions are repeating themselves, sodium ions are repeating themselves. Then what is the leftover? This is what's the leftover. Okay, your net ionic equation, that's the leftover. Okay, then whenever you have a strong acid react with the strong base, this is always your net ionic equation. Just remember that. Okay, then whenever you were given an example involving a strong acid with a strong base, if you did not get this as your net ionic equation, you made a mistake somewhere and you need to go and fix it. Let's do an example. Okay, then what we're going to do here, we're going to write a complete or balanced molecular equation. Okay, for the reaction between nitric acid, plus lithium hydroxide. Okay. Acid and bases are always in aqueous state. Know that. Okay, acid and bases, regardless of the strength of it, they're always in aqueous state. Okay, now I have nitric acid react with lithium hydroxide, which produces lithium nitrate and liquid water. Okay, remember, whenever we have an acid react with the base, the product is always aqueous salt and liquid water. Okay, Then once you know the product, you will have to make sure that's balanced. Then we have one lithium on each side, one nitrate ion on each side. We have 2 hydrogen on each side and 4 oxygen on each side. Then this equation is already balanced. You don't need to balance it. Next, we want to write our ionic equation. Okay? Let me choose a different color. All right. Nitric acid. Nitric acid is a strong acid. That means it will undergo 100% ionization, or it will separate. Then it will produce, remember, instead of hydrogen ion, we have to add right hydronium ion. Okay. That's for nitric acid. Now lithium hydroxide. Lithium hydroxide is also a strong base. Therefore, it will undergo 100% separation, which produces lithium ion and hydroxide ion. Okay. Now lithium nitrate. It's an ionic compound. It's in aqueous state. Ionic compound in aqueous state, they will undergo separation, which produces lithium ion plus nitrate ion. Now for water. Remember, liquid solid gases, they do not separate. Just leave it as is. But instead of one, we will have 2 water molecules. One is coming from here. The second one is for hydronium ion. Remember, to balance the hydrogen and oxygen, for every hydronium ion that we add, we have to add a molecule of water on the opposite side. Then one's coming from here and one's coming due to the production of hydronium ion. Therefore, I have 2. Sorry about that. Liquid water. Okay? And this is our ionic equation for this reaction. And last one is the net ionic equation. Okay? Now, let's look at the spectator ions. The nitrate ion is a spectator ion. Lithium ion is a spectator ion. Okay? Right, then whatever is left over will be our whatever left over is the net ionic equation. Okay, which will be hydronium ion plus hydroxide ion, which gives 2 water molecules. This is the net ionic equation. Then look here. I had a strong acid react with this strong base. Remember in the previous slide I told you guys, whenever you have a strong acid reacts in the strong base, this will be your net ionic equation. There you go. This is our net ionic equation. Okay? Here. Okay? And this is again our net ionic equation. Alright. Let's continue to the second example. Now let's do this one. We want to write a balanced molecular equation for the reaction between hypochlorous acid, calcium hydroxide, okay. Then you produce about that. I don't know why it's doing it. This is calcium. To aqueous. Plus liquid water. Okay, and it's just, we have a reaction between acid and base. That's your product. All right, now let's balance it. I have to add a coefficient 2 in front of hypochlorous acid. Okay, because just to balance it, because we have 2 on the product side, I have to have 2 on the reactant side. And also I have to add a coefficient 2 in front of water, because I will have 4 hydrogen on the reactant side, and I need to have 4 hydrogen on the product side. And I have 1 calcium on each side, and I have 2 and 2 oxygen on each side. Then this is balanced. Okay. Now, let's write our ionic equation. Okay, hypochlorous acid. It's a weak acid. Okay, it's not a strong acid. It is a weak acid. Weak acids do not separate. Just leave it as its own. Now, calcium hydroxide. Calcium hydroxide is a strong base. It will separate, which produces calcium ion and hydroxide ion. Okay. Now let's go to the product side. This compound right here, it's an ionic compound. It's in aqueous state. Therefore, ionic compound in aqueous state, they will separate. Then it will produce calcium ion okay. Now let's see the last one. Water in liquid state. It remains unseparated. Okay, just remains as is. Okay. Then this is your ionic equation for this reaction. Now let's look at the spectator ions. Calcium ion is our only spectator ion. We have no other spectator ion. Therefore, our net ionic equation the net ionic equation will be ion then this is our net ionic equation for the above reaction. Okay. As you could see, these two, remember net ionic equation is the simplified version of it. Then these two will get canceled out. Okay. Then if all these two get canceled out, we will end up with because the 2's needs to be simplified. And this is our final net ionic equation. Okay. All right. Let's do example 3. Example 3, you're going to write, again, a balanced molecular ionic net ionic equation for the reaction between hydrochloric acid and copper 2 hydroxide. Okay? Molecular equation. Basically balanced one, okay? All right. You want it to be between hydrochloric acid and copper 2 hydroxide. And you're told in this specific example that the state of copper 2 hydroxide is solid. Okay? That's what you have to do it. Because you're told the state of it is in solid. It's not aqueous. Right? Now what do you get? Okay? It's any acid base. Then you will get copper 2 chloride plus liquid water. Don't let the state of copper 2 hydroxide to confuses you. Okay? What we have is a reaction between an acid and a base. Your product is always going to be aqueous salt and liquid water. Okay? Keep in mind that. Again, don't let that solid state for copper 2 hydroxide confuses you. Just treat it as any acid-base reaction, which the product is aqueous salt, liquid water. The next thing that we have to do is to balance it. We have 1 copper on each side. We have 1 chlorine on this side, 2 on that side. That's why I add a coefficient 2 in front of hydrochloric acid. Now let's do hydrogens. I have 4 hydrogen on the reactant side, 2 on the product side. Then if I add a coefficient 2, I will have also 4 hydrogens. And now for oxygen, I have 2 oxygen, 2 oxygen. Then this equation is balanced. This is our balanced molecular equation. Now, I'm going to do the ionic equation. Okay? Let's go purple. Hydrochloric acid, strong acid. It will undergo 100% ionization or separation. Then what do you get? We get 2 hydronium ion. You see that too? Then instead of 1 hydronium ion, we get 2 hydronium ion. And we also get 2 chloride ion. Okay? Because of that 2 right here. Then, for copper 2 hydroxide. Even though our copper 2 hydroxide is a base, but since the state of it is in solid, we keep it intact. That means it will not separate. I'm going to write it as copper 2 hydroxide. Okay? Remember, solid liquid gases do not separate. Okay. Now this one. Copper 2 chloride. Ionic compound in aqueous state. Therefore, it will go 100% separation. What you will get copper 2 ion plus 2 chloride ion. Okay? Now, water. It's in liquid state, it will not separate. We have 2 water molecules. And look here. I had 2 hydronium ion. Remember, for every hydronium ion that's produced, we add a molecule of water on the opposite side. Then we have to add 2 water molecules on that side. And 2 is coming from here. That adds up to 4 water molecules. Okay? And 2 is because of the hydronium ion. And 2 is from our own reaction. Adds up to 4. Okay. Now let's do that ionic equation. Okay, let's go see if we have any spectator ions. Yes, we only have 1, the chloride ion. That's our only spectator ion. Okay, now the rest will be going to your net ionic, your net ionic equation. Then this is our net ionic equation. Okay, then whatever is left over will be the net ionic equation. Okay, then the key is that do not let that solid copper 2 hydroxide throws you off. It's in solid state, keep it as is. Also, one other thing, copper 2 hydroxide is also weak base. Weak base, they do not separate. That's why we just keep it as is. One more problem. Then we're going to do the same thing for the reaction between this balanced molecular equation, acetic acid and sodium hydroxide. Okay, then let's do acetic acid. Okay, plus sodium hydroxide. Remember, whenever you have an acid reacts with the base, your product is always aqueous salt and liquid water. Okay. This is already balanced. We don't need to balance it because we have one sodium on each side, one acetate ion on each side. Okay, we have 2 hydrogens on each side and 1 oxygen on each side. Okay, then everything's balanced. For acetic acid, there are 2 different ways of writing molecular formula. One is that, or then whichever you write is correct. Then here, this is the hydrogen and that's the hydrogen. Okay, as I said, that's the hydrogens that are gonna come up, or it's the indication of these compound to be the acid. Okay, then whichever you write is correct. Okay, now let's write our ionic equation. Acetic acid is a weak acid. Weak acid do not separate, stays as is. Sodium hydroxide, it's a strong base, it will separate, which means it produces sodium ion and hydroxide ion. Sodium acetate. Sodium acetate, what is it? Ionic compound. Consists of sodium ion, acetate ion, a cation, and the anion is an ionic compound. What's the state of it? It's in aqueous. An ionic compound in aqueous state, they will undergo separation, which produces sodium ion plus acetate ion. Okay, now water. It's a liquid, just keep it as is. We're only gonna have one water molecule, no more, because we did not produce any hydronium ion. We only do that if we produce hydronium ion. Since acetic acid was a weak acid, it did not separate. We did not produce hydronium ion. That's why we don't need to add any water molecules. Then we only have one from the above reaction. Alright, now that we know what's our ionic equation, let's write the net ionic equation. Okay, to do that, let's go look for spectator ions. We only have one, and that's sodium ion. Everything else will not cancel each other out. Then the remaining is this, the remaining will be your net ionic equation. Okay, that's your net ionic equation for the reaction between acetic acid, which is a weak acid, and sodium hydroxide, which is a strong base. All right. Now the third type is a redox reactions or oxidation reduction reaction. Whenever we have an oxidation reduction reaction, which we also call them as the redox reaction, there is a transfer of electrons. Okay. Whenever we have a transfer of electrons, that reaction is always a redox reaction. That means one of the reactants gonna get oxidized, another reactant's gonna get reduced. Okay. The examples when you go to the hair salon and bleach your hair, or if you leave your bike outside over the winter and you go back to it, it's all rusted out and looking ugly. These are all indication of the transfer of electrons, which we also call them oxidation reduction reactions. Okay. A lot of redox reactions, oxygen is one of the reactants. Okay. Then whenever you see oxygen as one of the reactant, that reaction is a redox reaction. Okay. Then when oxygen gas sorry about that, is one of the reactants, that reaction is a redox reaction. Okay. Then whenever you see oxygen as one of the reactant, that reaction will be a redox reaction, which you will see in my next couple of examples. I will have redox reaction, and you will see that there's a reaction with oxygen, and we have a transfer of electron. What does it mean by redox or oxidation reduction? Then oxidation is the loss of electron. That means one of the reactants that's losing the electron, it's becoming oxidized. And the second reactant that's gaining the electron, it's a reduction. Okay. Then it happens between the reactants, not the products. And the reactants that's losing the electron, it's becoming oxidized. And the second reactant that gaining that electron that's being lost by the first reactant, it's becoming reduced. Then for example, if this is reactant A, let me change color. Reactant A, and this one is reactant B. Then what happens is that reactant A loses the electron, it becomes oxidized, and reactant B gain that electron, it becomes reduced. Okay. Then one species, when one of the reactants become oxidized, there should be another reactant becoming reduced. Okay. We cannot have two oxidation or two reduction. Always one of the reactants being oxidized, the other one being reduced, and vice versa. That's a really good, helpful hint for knowing which one is reduction, which one is species is oxidized. Then remember that oil rig, okay? Which oil, it means oxidation is loss of the electron, rig, reduction is gain of electron. There is other ones, so many other hints to denote that, but I've always known this one and I've always used that one, okay? Oil, rig. Oil is loss of electron, rig is gaining electron. Now, what's the difference between oxidizing and reducing agent? Remember, going back here, reactant A lost the electron. Then when it loses the electron, it becomes oxidized itself. But it's going to help reactant B to get reduced. Okay? Then going back here, okay? Then reactant A, going back to our previous example, that's what I'm trying to do. Okay? Then reactant A was oxidized. Then what happened is that it helped reactant B to get reduced. That's why reactant A is oxidized, but it's also a reducing agent. Okay. Actually, I should have written this one here. Okay. Let me do that here. Okay. Sorry about that. Then what happens is that reactant A is becoming oxidized. Okay. A is oxidized. Then once it's oxidized, that means losing the electron. It helps reactant B to get reduced, right? That's why reactant A is oxidized, but it's also a reducing agent. That means it's going to help reactant B to get reduced, and vice versa. Reactant B is reduced, but it's going to help reactant A to get oxidized. Then reactant B is reduced, but it's an oxidizing agent. Reactant B is reduced, but then it becoming an oxidizing agent. Okay. Then the reactant that becomes oxidized, it will also be a reducing agent, and the reactant that's being reduced will becoming an oxidizing agent. Okay. Now let's do this problem. What you want to do for this particular example is to tell me which reactant is reduced, which one is oxidized, which one is a reducing agent, which one is the oxidation agent, and how many electrons are being transferred. Okay. Then what it is that magnesium, okay, the magnesium reacts with, when it says burned in air, that means it's reacting with oxygen. Okay, what is the element that you need for a substance to burn? Oxygen. So when you ever hear something is burned in air, that means that reactant is oxygen gas, and it produces magnesium oxide, and you're told it's solid. Okay, then this is a chemical reaction when magnesium reacts with oxygen, which produces magnesium oxide. One thing that we want to do is to balance it. Okay, we have 2 oxygen on the product side, we have 1. What we could do, we could add 2, and then if I add 2, this will be balanced. Okay, I have 2 magnesium, 2 oxygen, 2 magnesium, 2 oxygen. Once you have that balance, now what we're gonna do, we're gonna look for, or we're gonna assign oxidation number for each of the reactants and products. Okay, step 1, we're gonna assign oxidation number for charge for each element. Measurement on both sides. Okay, that's what we're gonna do. All right. Then elements on their own. Elements on their own. And diatomic compound, these, their oxidation number is 0. Okay, is 0. Okay, then elements on their own and diatomic compounds, their oxidation number is 0. Okay, then elements on their own, magnesium on its own, okay, its oxidation number is 0. It's not charged, basically. Okay, diatomic compound, also their oxidation number is 0, or they are not charged. Okay, now magnesium oxide. What is the charge of magnesium oxide? Magnesium is in group 2 on the periodic table. Its charge is +2. Oxygen is in group 6. It's -2. Okay. Okay. Then charge or oxidation number has nothing to do with balancing. These are two separate topics. Then once you know the charge on each of the species, then what you want to do is to look for the charge for magnesium on both sides. Okay, look here. The oxidation number or charge for magnesium went from 0 to +2. When it goes from 0 to +2, that means it has lost electrons. Okay, electrons, they contribute to negative charge. Okay, then when you add electron to a species, its charge becomes more negative. If you remove the electron from a species, it becomes more positive. Okay, then here magnesium went from 0 to +2. That means it's losing electron. It's becoming more positive. That's why it's getting oxidized. By how many electrons? It went from 0 to 2. Okay, or it lost 2 electrons. Remember oil rig? Okay, oxidation is loss of electron. Magnesium went from 0 charge to +2 charge. Okay, it lost 2 electrons. That means it's oxidized. Now let's look at oxygen. What happened to oxygen? Oxygen went from charge 0 to -2. Okay, from 0 to -2. Remember, electrons contribute to negative charge. That means it's becoming more negative. Okay, becoming more negative. That means it's gaining electron. Reduction is gain of electron. That means it's reduced. By how many electrons? How many electron is gained? It went from 0 to -2. That means it gains 2 electrons. Okay. Okay, once we have that figured out, now let's write it up. Let me choose blue color. Okay, Then what we want to know, which species is reduced, which element is oxidized. Okay, then oxidized, it's magnesium. Remember, we only assign it to the reactants, not the product. Which one is reduced? It's the oxygen gas. Now, which one is the oxidizing agent? Which one is the reducing agent? Okay. Then oxidizing agent, reducing agent. Remember, the reactant that's being oxidized, it's our reducing agent. And the reactant being reduced is the oxidizing agent. Okay, then here magnesium goes from oxidation number 0 to +2. It's becoming more positive, which means it's losing electron. Losing electron, it's becoming more positive, it's oxidized. Oxygen gas goes from 0 to -2. It's becoming more negative, it's gaining electron. Gaining electron is reduction. By how many? 2. Then magnesium is being oxidized, oxygen is being reduced. That reactant is oxidized, it becomes a reducing agent, and that reactant that's reduced becomes an oxidizing agent. Now, how many electrons are being transferred? Okay, give me 1 second. Then magnesium has lost 2 electrons. Oxygen has gained it. Then how many? 2. Then transfer of electron. It's 2. Okay, because magnesium lost the 2, oxygen got that 2. Then we have 2 electrons being transferred. If it would have been 2 and 4, we'll go with 4. If it would have been 3 and 2, we go with 6. Just use the common factor. Okay, but here is only 2. Now let's do one more example. Okay, which is copper 2 chloride reacts with hydrogen gas and it produces hydrochloric acid, gaseous hydrochloric acid, and copper metal. Okay, and what you want to do to balance it, we have 1 copper on each side, we have 1 hydrogen, we have 2 hydrogen on this side, then I added coefficient 2 here. Now I have 2 hydrogen, but now I need to have 2 chlorine because now I have 2 and I have my 2 chlorine. Okay, then as you can see, this is balanced. I have 1 copper on each side, 2 chlorine on each side, 2 hydrogen on each side. Now once you have that balanced, okay, now let's assign oxidation number. For copper 2 chloride, okay, you already told its oxidation number is 2, but in case if you could not do it, okay, copper 2 chloride, okay, then this compound consists of 2 copper plus 2 chlorine. It's a neutral charge compound, that's why the sum of charges has to be 0. Now we're going to solve for copper. Then it's 2 copper, we don't know what its charge is, plus we have 2 chlorine, or chloride ion, then group 7 are -1, the sum of charges is 0. Therefore, now solve this equation. 2 copper minus 2 becomes 0. Okay, you know what mistake I made? It's not 2 copper, it's only 1 copper. Look here, it was only 1. It's 1 copper 2 chloride ion. Okay, that was a mistake that I made. There is no 2. Then going back, this compound consists of 1 copper ion, 2 chloride. It's a neutral charge compound. That's why the sum of charges is 0. You don't know the charge for copper. Okay, that's just only 1 copper. You do know the charge for chloride, or it's in the group 7, it's -1. Okay, then if you solve it, copper -2 is 0. That's why copper is +2. Okay, remember, copper is a transition metal. It has so many different oxidation number. Then in this particular example, it's +2. And you're told here is copper 2. Okay, then you didn't even need to solve. All right. Then copper is +2. Chlorine is group 7, -1 is charge. Remember, diatomic compound is 0. Now, hydrogen. Hydrogen sometimes have a +1 charge, sometimes has a -1. If it reacts with a metal, okay, let's do a side note. Okay, here the charge on hydrogen is -1 because sodium is +1, hydrogen is -1. Okay, then when hydrogen is reacting with a metal, okay, it will be -1. If it's reacting with a non-metal, like this example, chlorine is a non-metal, it becomes +1. Again, chlorine is -1, is in group 7. An element on their own, their charge is 0, or their oxidation number is 0. Okay. Again, oxidation number has nothing to do with balancing. Okay. Totally two different topic. All right. Now, copper has a change of charge. Chlorine didn't have it. Okay, it was -1, it's -1. Hydrogen also did. Then what happens here? Copper went from +2 to 0. Again, let's write our hint. Oil rig. Oxidation is loss of electron. Reduction is gaining an electron. Copper went from +2 to 0. It's becoming more negative. You see that? Okay, it's becoming more negative. It was +2, now it's becoming 0. It's going toward the negative side. Okay, if this is 0, that's 1, 2, 3, etc. Here is -1, -2, -3, etc. Then copper was here. Now it's here. You see, it's going more toward the negative. Okay, then if it's going more toward the negative, what does it need? It needs electron. It's gaining 2 electron to go from +2 to 0. And what is the gain in electron? Is reduction by 2 electron. Okay, now hydrogen. Hydrogen was 0, it went to +1. Then hydrogen was here, now it went here. As you could see, it's becoming more positive. Once it's becoming more positive, that means it's losing electron. Okay, it's losing, which is oxidizing. Okay, oxidizing, it went from 0 to +1 by 1 electron. Okay, now we want to assign, once you have that figured out, what I'm gonna do next is to figure out which species getting oxidized. Let's write it down. Oxidize, reduced, oxidizing agent, reducing agent, and number of electron being transferred. Then which species becoming oxidized? Remember, we only assign it to the reactant, hydrogen. Hydrogen is oxidized. It went from 0 to +1. It lost electron. Then hydrogen gas. Which one was reduced? Look at copper 2. It went from +2 to 0. It's becoming more negative. That means it's gaining electron, okay? Or reducing. You could write copper 2+, okay? Or copper. But it's better to write copper 2+. Remember, we assign it to the reactants. If you write copper, it will kind of not sound right because you're assigning it to the product. That's why I just leave it at copper 2. Also, don't write copper 2 chloride, because if you say it's this, that is not right. Why isn't it right? Because nothing happened to chlorine. Okay, it's not chlorine that became reduced, it's copper 2 that became reduced. That's why the most proper way of writing this is just write it copper 2. Now, the species that's becoming oxidized, it's the reducing agent. The one becomes reduced is our oxidizing agent. Now, how many electrons becoming transferred? It's 2 and 1. 2 is reduced, 1 is oxidized. Then what's the common factor between 2 and 1? Is 2. Then we don't add, okay? We don't multiply. We just use the common factor. 2 and 1 is 2. 2 and 4 is 4. 3 and 2 is 6. Okay? 5 and 10 is 10. Then we don't add, we don't multiply, we don't divide. Use the common factor. Between 2 and 1 will be 2. Okay. Then as you could see in the previous reactions or the previous examples, oxidation and reduction happened at the same time. Okay? That means here, copper gained 2 electrons. Okay? Hydrogen gas lost the electron. Okay? Then copper got reduced, hydrogen gas become oxidized. Okay? Then redox reactions happen at the same time. One of the reactants become oxidized, the other reactant become reduced. Because when one of the reactant is losing electrons, something has to gain those electrons. Okay? That's why it's the second reactant. Then once it gains those electrons being lost by the first reactant, that itself become reduced. Okay? Then it is important that we cannot have both of our reactant getting oxidized or both having reduced. One reactant always get reduced, one reactant always get oxidized. Okay? Then they happen simultaneously at the same time. Maybe let's put a highlighted here. Okay? They must happen together. Okay? Then when one substance loses the electron, then the other substance, by substance means reactant, gonna gain that electrons. All right. Then how would you know which of the reactions are redox? The first one, whenever oxygen gas is one of the reactant. Okay? That's a redox reaction. When you have a metal reacts with a non-metal, that's a redox reaction. Why? Because the metals like to lose the electron. Non-metal likes to gain the electron. Okay? Then when metal loses the electron, they become oxidized. Non-metal gain the electron, they become reduced. Right? Okay? And basically, whenever you see there has been a transfer of electron, that reaction is a redox reaction. Okay? Basically, the keys, one of the two obvious reasons, when oxygen is one of the reactants and when you have a metal reacts with the non-metal. For the rest, just assign oxidation numbers as I did in the previous example, as I did here. Okay? In this example. I signed oxidation numbers. And then the ones that they have a change in oxidation number, they undergo redox. All right. Last one is gas. It's a formation of gas, or which we call it combustion. Okay, when you have a combustion reaction, that means we are forming gas. All combustion reactions are redox reactions. Okay, all combustion reactions are redox reactions. Because combustion basically is the process of burning. Okay, what do you need for a substance to burn? What's the key element for burning? It's oxygen. Okay, then if you recall, when something is on fire, what do we say? We say we cover it with a heavy blanket. That way we prevent the oxygen to getting in. Okay, then combustion reaction involves burning, involves reaction with oxygen. That's why it's a redox reaction. Okay, combustion reaction, which is burning, it produces heat. If you go and stand in front of the fire, you will sense the heat that's coming off of the fire. Okay, that's why it's an exothermic reaction, because they produce heat. Formation of water, it's also a combustion reaction. It's also a redox reaction. Okay, here, if you assign oxidation number, right here, hydrogen, remember diatomic compounds, their charge is 0. Okay, their oxidation number is 0. Now look here, hydrogen is +1, oxygen is -2. This is a redox reaction. Oxygen goes from 0 to +1. What is it? It's losing electron, okay, which is oxidation. O2. Okay, let me see if I could do it here. Yeah. Oxygen going from 0 to +1. It's oxidizing by 1 electron. Okay, now let's look at the second one, oxygen. Okay, oxygen's going from 0 to -2, becoming more negative. It's gaining electron. It's getting reduced by 2 electrons. You see, this is also a redox reaction. Here, hydrogen is being oxidized. Oxygen is being reduced. Hydrogen gas is your reducing agent. Oxygen gas is your oxidizing agent. And we have a transfer of 2 electrons. Okay, 1 and 2, the common factor is 2. Okay, then whenever we have a combustion reaction, they are all redox reaction because it produces gas. Okay, and combustion reaction, do you need oxygen as one of the reactants? Basically, combustion means burning. Okay, then combustion means burning, and that's what it means, burning. And burning means reaction with oxygen gas. Okay, that's why all combustion reactions are redox reaction. Okay, and they're also exothermic because when you go and stand in front of the fire, you feel the heat that's coming off of it. All right, whenever we have organic compounds, basically what do I mean by organic compound? Okay, organic compound means it has carbon in its skeleton. Okay, a skeleton or part of chemical formula. Okay, whenever you see carbon part of a chemical formula, that compound is an organic compound. Okay, like here, methane is an organic compound because it has carbon as part of its molecular formula. Then when you have an organic compound undergo combustion, which is reaction with oxygen, the product is always carbon dioxide and water. Okay, know that. Another one that we've talked about is sugar. Okay, C6H12O6. Okay, that's also is a combustion reaction. Remember, respiration. Okay, we get respiration. What it is? The food and the oxygen in the air. What do you get? Carbon dioxide and gaseous water. Okay, then whenever you have an organic compound, it reacts with oxygen in the air, which we call a combustion. The product is always gaseous carbon dioxide and gaseous water. Okay, that's the rule. Now, following the previous talk about combustion of organic compound, now let's talk about aerobic and anaerobic conditions. When we have aerobic conditions, that means we have access to a lot of oxygen gas. Okay, then for example, let's go to that methane example. Okay, when we say it's an aerobic condition, that means we have access to a plenty of oxygen, a lot of gas. Then what you get as your product will be carbon dioxide and gaseous water, right? That's what we had. Then to balance it, we have 2 hydrogen on the product side, 4 on the reactant side, 2 on the product side. I add a coefficient 2 in front of water. Now I have 4 hydrogen and 4 hydrogen on the product side. Now carbon is fine. I don't need to change carbon. I have 1 carbon. Look at oxygen. I have 2 oxygen on the reactant side, but I have 2 and 2, which is 4 on the product side, which I add a coefficient 2. Okay, that's for when we have plenty of oxygen, or when there is an aerobic condition, that means access to a lot of oxygen gas. Then for any organic compound in aerobic condition, it will be carbon dioxide and gaseous water. Now, anaerobic condition means we have a little or limited or no access to oxygen. Then in that case, instead of carbon dioxide, we have carbon monoxide. Okay, that's the difference between aerobic and anaerobic condition. Okay, in aerobic condition, we have carbon dioxide, and in let's choose a different color. And in anaerobic condition, we have carbon monoxide. Okay, when it's aerobic condition, that means we have access to a lot of oxygen gas. That's why the product is carbon dioxide. In anaerobic condition, we have limited or no oxygen gas. That's why the product is carbon monoxide. Water stays the same. Okay, everything stays the same. The only thing that changes, it's aerobic condition is carbon dioxide. Anaerobic condition, carbon monoxide. Okay, know that, memorize that. This equation is not balanced. What we have to do is to balance it. Okay, Then as you could see here, I have 4 hydrogen here. I have 2. That makes it 4. Okay. Now, I have 3. Okay, I have 3 oxygen. What you could do, remember, I went over that in class. You could go 3/2 here, but coefficient has to be a whole number. It could not be a fraction. Okay, 3/2 times 2 is 3. Okay, because these 2's cancel out. Okay, then what we have to do, let me make it more room here. Since we cannot have a fraction, we have to do something to get rid of the fraction. In order to get rid of the fraction, if I multiply everything by 2, I could get rid of the fraction, right? Then I'm going to multiply every single coefficient by 2. Then 1 times 2 is 2. 3/2 times 2 is 3. 1 times 2 is 2. And 2 times 2 is 4. Okay? Right? Then that's why I have these coefficients. And as you could see, I have 2 carbon on each side. I have 6 oxygen on each side. And I have 8 hydrogen on each side. Then whenever you have difficulty balancing, use coefficient, but make sure to get rid of your coefficient as I did in this example. Then one more time, when we have a combustion reaction, it's a reaction involving oxygen. It's a process of burning. What do you need? We need oxygen. Combustion reactions are exothermic. Combustion reactions involving organic compounds, those compounds that contain carbon as part of their formula, the chemical formula, the product will be carbon dioxide and water. But we will have 2 conditions. One is aerobic condition. In aerobic condition, we have access to plenty of oxygen gas. That's why your product will contain carbon dioxide. In anaerobic condition, you have access to limited or no oxygen gas. That's why the product will be carbon monoxide. Everything else remains the same, as you could see. It's only the carbon dioxide and monoxide. If it's aerobic, carbon dioxide. Anaerobic, carbon monoxide. And as always, you have to make sure your equation is balanced. Okay. All right. So just let's go over it. When we are talking about chemical reactions in Chemistry 130, we have precipitation reactions. That's when we have solid as one of the product. We talked about acid-base reaction, which is a reaction between an acid and a base. Then whenever we have an acid react with a base, regardless of the strength of your acid or base, your product is always aqueous salt and liquid water. For oxidation reduction, which we have a transfer of electron, oxidation is losing electron, reduction is gaining electron. And combustion reactions, which are type of redox reaction, it's a reaction involving oxygen. That means oxygen will be one of the reactant. Okay, all combustion reactions are redox reaction, and they are exothermic because burning, what does it produce? It produces heat. Also, chemical reactions are split into synthesis, which when we are synthesizing something, it means we are making a product. Decomposition, it means we are separating the product. We have single and we have double displacements. Okay, these are examples. When we have synthesis or combination, as you could see here, we are making a product. That means reactant A reacts with reactant B and it makes a product, just one product. Decomposition, that means it's a separation of the product into the element that it came out of, right? Now, single displacement, as you could see here, like A reacts with BC. We get AC and B. And double displacement is this one. A lot of the problems that we did here, a lot of it was double displacement. Basically look at how which one follows one format, and you will know if it's a single displacement or double displacement, or synthesis or decomposition. Okay, I'm done teaching chapter 7. It's complete.